Okay, we are going to look at a couple related rates problems today. You can take notes for this in your regular notebook, and then you can think about how you want to take notes. You could certainly just write these problems down as examples to refer back to, or as you watch the video, you could kind of draw out what are the general techniques that are happening here and take notes on sort of the general approach for related rates. Kind of the choice is yours in terms of what would be the most useful notes to take. All right, so let's jump in here. All right, so related rates is about using derivatives to answer questions. So the first step in any problem, once you read it through, is to draw a picture if a picture is not provided. So here we have a kite 100 feet above the ground being blown away from a person holding its string. So I'm just going to draw that. Here's the ground. Here's the kite. And then there's a person over here holding the string. I'm going to figure the difference between the ground and where that person is holding the string is negligible, since we're talking about distances of 100 feet, and a person wouldn't be anything very close to that. All right, so there's my drawing, and the kite is 100 feet above the ground. And we want to label some other things about this diagram. So I'm going to label this side of the triangle X and this side of the triangle Y. And then my general approach when doing related rates is to use an acronym PIG, which you might have learned last year. P stands for permanent, so I write down what's permanently true. I is instantaneous, I write down what's instantaneously true. So true in the moment, instantaneous. And G is for get. Okay, so as I read through and write down information from the problem, it gets sorted into one of those three PIG categories. All right. So the first thing I can do, what's permanently true, is a relationship in this triangle, which is that x squared plus 100 squared equals y squared. So just the Pythagorean theorem. And the kite is being blown away parallel to the ground at the rate of 10 feet per second. So that means x is increasing. So dx dt is 10. If it was going towards the person, it would be negative 10. At what rate must the string be let out when the length of the string is already 200 feet? So instantaneously, in the moment, y is 200. But that's not permanently true. It's just true in the moment we're looking at. And at what rate must the string be let out? So we're asking, at what rate is y changing dy dt? So I've got permanent, instantaneous, get. And the reason we differentiate between permanent and instantaneous is that y equals 200, you would not want to substitute here before you do any calculus, because it's only true in the moment, whereas this 100 is always 100, so that can be put in to the equation before you do any calculus. So don't substitute before you do calculus values from the instantaneous column. All right, so let's do some calculus. So I've got dx dt and I want dy dt. So my equation has x and y, so I'm good to go. So let me write down my equation again. X squared plus 100 squared equals y squared. And what I'm going to do is I'm going to take the derivative with respect to t of both sides. So t is not generally in the original equation, but related rates is all about rates with respect to time generally. All right, so if I do that, that would be 2x, and then since it's not a t, I have to do the chain rule, the derivative of x with respect to t. Derivative of 100 squared is 0, and similarly on the other side I have 2y dy dt. All right, so once I've done the calculus, then I can do the sum. All right. Oh, and I don't have x. However, I can figure out x because instantaneously y was 200. So that means x squared plus 100 squared equals 200 squared. So x squared is square root of 200 squared minus 100 squared. I can factor out a 100 squared. Oops, no more squared. So if I take out the 100 squared from the square root, I have 2 squared minus 1 squared, or 100 root 3. Okay, so now I can substitute. So for x, I would put 2 times 100 root 3, and then dx dt we said was 10. And then for y, 2 times 200 times dy dt. So usually once you substitute, solving for what you want to get isn't too bad. So that would mean dy dt would be 2,000 root 3 over 400. Am I doing that right? Let me just double check my numbers and my calculations. Okay. And so 2,000 divided by 400 is 5 root 3. So there is my answer. Missing the equal sign. Okay, so that's our first related rates problem. So now we can apply that same process in another example to see what's the same and what's different. So in our second example, sand is dumped off a conveyor belt into a pile at the rate of 2 cubic feet per minute. The sand pile is shaped like a cone whose height and base diameters are always equal. At what rate is the height of the pile growing when the pile is 5 feet high? So I hear a lot of both P, I, and G there. So again, first thing I do is start with a picture of a cone. There's the height. There's the diameter. P, I, and G. All right, sand is dumped off a conveyor belt into a pile at the rate of 2 cubic feet per minute. That means the volume is increasing. So dV dt equals 2. The sand pile is shaped like a cone whose height and base diameter are always equal. So that means H is always equal to D, which is the same as 2R. So that's a permanent relationship. At what rate is the height of the pile growing when the pile is 5 feet high? So since it says when, that's instantaneously. H equals 5. And then they also helpfully give us this volume equals pi over 3 r squared h. Okay, and I think we pulled out all of the information except what we want to get. At what rate is the height of the pile growing? So we want to get dh dt. So looking at the derivatives you both have and want can be really instructive. We have dv dt, we want dh dt, so I need an equation that relates v and h. So this is a good start, but it's got too many variables. And that often happens, where the equation that has both the variable you have and the variable you want for the rates has extra stuff in it. So we have to do a little bit of algebra. So then I would do a substitution. It looks like from this equation, r equals h over 2. So then I would have 12 pi and h to the third. All right, so now I have an equation just with v and h. So then if I take the derivative of both sides, I have to squeeze that in there. There's still an equal sign there. Then I can get that relationship. So dv dt equals, use the power rule, so pi over 4 h squared, and then chain rule dh dt. Okay, and notice I didn't use that 5 value yet, but now that I've done the calculus, I can substitute the instantaneous value. So let's see, what do I know? dv dt is 2, pi over 4, h is 5, and I want dh dt. And so then dh dt multiplied by 4 divided by 25 pi, and I think I'm done. So there is my final answer. All right, I'll zoom out so you can kind of take a look at it all, see if you want to write down any final notes about the process, and we are done.